The way we experience things is highly subjective and a very human perspective. This video is a journey through the things we don't experience when we're using these machines. The stuff we take for granted, in some cases the reason things happen that we may have observed but we do not know the cause. When you get in close and you slow down, things look different. We'll go into the things that we're doing and the things we're seeing, and some cool technical information behind how I did it. That is your warning if you're one of those people who objects to a free lesson in photography. You can leave while the rest of us join me for something a bit different. Let's go. This video is sponsored by PCBWay. A lot of printers these days do a shaking thing when they calibrate before a print, or maybe just once when they calibrate independently. You might know what this is already, or you might just think it's a routine to try and shake off any bogeys off the nozzle. It's not. If you would like a video specifically on input shaping, that would be cool to do. Comment below. The brief version is that it's an open loop control technique, meaning the control system doesn't gain real-time feedback for reducing vibrations. You're trying to disrupt those vibrations. The point is to be able to create a function that will cancel them out. You have to know what those vibrations are doing to the system though in order to be able to do that, because the printer in this case will shake differently at different vibration frequencies. You probably know them as resonant frequencies. That's actually all there is to it. So the various shaking processes that the printer is doing is happening at the same time as an accelerometer somewhere is measuring the corresponding amplitude of that shaking in all three axes preferably, and this is what gives you your graph, which can be interpreted simplistically as how much this thing resonates by frequency. The idea then to join all the dots together and give you the full picture, you would use a control algorithm that moves the toolhead in a manner that best avoids the resonance spikes that we see in the graph. Ideally, you don't want to see any resonance at all. Before I show you the most exciting part of this video, I will show you something disturbing. This is just PLA. I've overheated it on purpose, but not by much. In fact, this phenomenon happens a lot while purging because the nozzle tends to overshoot a lot during that time depending on your machine and the kind of hot end you have. It isn't normally visible because of the lighting. If this doesn't convince you that you need to ventilate your room when you're printing, then I don't know what will. This smoke is definitely not good for you. And imagine if that's happening every time you change colour. So purging is used a lot to change colour. I can show you that in slow motion under macro. Now, if you saw that and you thought, hang on a minute, something going on here, you would be right. Let's back up a bit and look again. Do you see what's happening here? More than one thing is happening, actually. The first is that the filament is changing from the middle outward. This is something that we know happens. I've talked about it before. There's been several papers written on exactly this. There is a tendency for filament to flow faster in the center of the nozzle than the edges. This is ultimately due to drag. This is, to my knowledge, the first time anyone's shown it on a 3D printer on camera, though. So I'll also make it the second time by showing you it again. And we'll do a third time. You can see it's causing the old filament to bulge out because of dye swell, even though you can't see the new filament coming through. You can see what it's doing. But going back to the colour change, there's more going on here. Did you notice that the colours just do not mix at all? This is laminar flow happening while we watch. The reason why this happens is because the filaments are both so viscous that a turbulent flow isn't induced. In fact, it is near impossible to create turbulent flow with filament, which is why you can't put two filaments in and get a mixed colour out, in spite of how much you might try. And it's why tricolour filaments are a thing, and it's why we don't have RGB mixing of filaments yet, even in 2 input, 1 output nozzles. I thought Prusa's animation on the new Core 1 was pretty clever. I thought I could make that on my own. It can't be hard, surely. In their version, the front cover is actually CGI, and they've added motion blur, which is a nice touch, but it makes it look a bit uncanny valley, I suppose. You can tell it's not the real front cover, or it's obvious to me. And behind it, the extruder is a real one, and it's actually moving. So this is how I knew I could get away with doing that without the extruder falling apart. But don't try this at home, because if you do, you might have to suffer the consequences if it chews itself up or something. I'm obviously more resistant to that. I initially thought that they'd edited out a piece of acrylic because you could still see the screws, but it's actually a lot simpler than that. They just put the screws back in to stop the brass part falling off. I think they used shorter screws as well. I printed a small black peg in order to hopefully not be too visible instead, and it's just the right size to be friction fit. Gluing a very thin string to the side of the panel, and this should absolutely work. I can pull it away. All I then need to do is edit my hand out and nobody will know. Perfect. Prusa, if you're hiring CGI artists in the future, you know where I am. Interestingly, it looks like they've drilled holes in the Core 1 version of the Extruder, which the Mark IV and Mark IV's one doesn't have. I do have a Core 1. I haven't taken the front off yet. Maybe I'll include it in the review, which is coming soon. Shenanigans aside, the whole point of taking the front off the Extruder was to look at it, so let's look at it. The fastest I can record at until I convince Kronos to send me a review unit of one of their, I don't know, they're like 10 grand cameras, I think. The fastest I can go is 1,000 frames per second. This is actually quite fast, but most cameras that you can get for YouTubing have a maximum slow-mo speed of 200 frames per second. That is fine. You might be yelling, my phone can do 960, but 960 frames per second on a phone, I think there's like one phone that can really do more than that, or can actually do that. When your phone is telling you 960 frames per second, it is making up a lot of data there. They call it interpolated because that doesn't sound as terrible as making it up, but ultimately it is. Made up frames or made up pixels don't work when you're trying to do real slow-mo to do analysis. So I have a camera that can do 300 frames per second at 1080p at high quality. This is kind of very much the edge of what anyone can do without bankrupting themselves. Or is it? There is one camera out there that can do 1000 real FPS, for real, no interpolation, and it's a bit of a unicorn, and it's this one. I don't think they sell these anymore. You have to hunt down used ones. I bought a used one, but they're quite common. They're quite easy to find. There is no free lunch, though. The 1000 frames per second you get off this camera is way lower quality than 300 off the other camera. And you can't do macro. You can, but you have to use a diopter lens and glue on an adapter. The biggest problem overall is the amount of light it needs. If you think about it, the 1000 frames per second means that the maximum length you can have of one frame is 1/1000th of a second. Otherwise, you can't get 1000 frames per second. So, yeah, the sheer amount of light that I had to use to get anything from this camera, I can't really explain just exactly how bright that is. Anyway, as you expect, I'm going somewhere with this again. Nextruder. Enderstruder. Notice anything strange here? The Ender one, you might have noticed, it ticks. It's not a clock. What you are seeing here is microstepping. It's actually quite fascinating. I didn't think we would be able to see that at all, but it's quite visible here, isn't it? The vast majority of extruders on most machines since 2020, they don't tick visibly. You won't see it. They're still doing it, but just way, way, way faster. There's finer grades of microstepping. I understand that the Ender 3 used by default 16 microsteps, so for every magnet inside the stepper you get 16 discrete positions. I did a video on this, it's called Steppers 2, go and watch it. If enough people watch it I might make Steppers 3, probably not. Incidentally, if you're wondering, this is where the pesky idea of magic numbers comes from. It's not relevant now, and it hasn't been for a long time, and to be honest, it possibly never was. Just as it's not relevant in the Extruder on the Ender 3. I still hear people talk about it though. I want to put this annoying myth to bed as well. These wheels are fine in the application of 3D printing. I can put a thing on screen there. These do not bounce around even when moving fast, which they are doing here. Wheels are fine. Stop complaining about wheels. Nothing is happening here on a scale that matters to FDM. Nothing. Let's talk about something that isn't slow, today's sponsor PCBWay. You would be surprised how quickly they can make your custom PCBs or other manufactured parts. PCBWay offers manufacture of PCBs from the very basic single layer or two-sided boards up to far more sophisticated multi-layer boards and assembly for insanely complex needs. There's no special skills required for the very beginner either. If you can figure out how to design a PCB, then that's the hard part done. And ordering it is the easy part, with most of the fields already pre-filled to the values you probably want. If I can do it, you can do it. I'd never designed a PCB before using PCBWay, even though I've got plenty of experience in electronics, and I managed. PCBWay can also manufacture parts using 3D printing, CNC manufacturing, and sheet metal bending. With respect to the first two, these are extremely approachable to anyone who knows how to design for 3D printing using CAD software, because the process and files are the same. You can upload a step file and get it made out of aluminium with a CNC process. There's lots of options. You should go and check them out. I'll put a link in the description where there's also a new user coupon. Thank you PCBWay for sponsoring this episode. Back to it. I think that most printers have a decent amount of rigidity, to the point that even when you slow them down, you don't see a lot of wobbling around. It's a testament to modern printers, I think, because there's really not a lot to see, and I thought there would be, but there wasn't. But there was one notable exception: Delta printers. There was another exception, and not where you would expect it. I think a lot of printers do this, probably all of them actually, but especially those where they move the bed instead of the gantry for Z movement. Watch this. Do you see it? Exactly, it's bouncing after every Z hop. This is way more reason to turn that off, unless you know that you need it. I think that's everything that I wanted to show you in this episode. There was a lot there. I didn't expect that much when going into this, so there you go. What did you think? What did you think about what you saw? What did you think about this video? Let me know in the comments. As always, I will see you next time with a Core 1 video, probably. Thank you for watching. And it's a bit of a unicorn, and it's this one.